Okay, so we're getting into the formal definition of a limit, and I have a video here that kind of really explains things and kind of ties together what a derivative is, which we haven't talked about yet, but we actually have looked at. Back in the first section we looked at the average rate of change and the instantaneous rate of change and trying to find the slope at a particular value. That right there, that slope at a particular value, that's basically what is called the derivative of a function at that point. And so when you're going to see a little bit of that first, explaining things, and then it's going to jump into explaining the formal definition of limits. And we've been looking at what limits are when we get really, really close to an x value on the left and the right. If we're approaching the same value, then that limit exists. Well, what does really, really close mean? And so mathematicians and philosophers struggled with this concept for a long time. And so they came up with this delta epsilon proof that they agreed, okay, that this works as a definition, as getting really, really close to, or approximately. And so we're going to start this video. If there's a problem, again, I'm going to just link this. This link will be on your course Canvas page to watch this video if for some reason you weren't here today during lecture and you need to watch it, or if for some reason it doesn't come through when I'm screening it very well, then we'll stop. You guys will go watch it. We'll come back to class in like 10 minutes. So let me start the video. I'm not going to record the video, so if again you miss class, you're going to have to go to the link and then watch it yourself. Okay, so that worked and you guys were able to see the video. And so again, if you are missing class and you're coming in and watching this video, there's a link to the video on YouTube for you to watch, which I thought kind of was cool, bringing in what we were learning with finding the slope of a tangent line. They were defining that more as a derivative, which we'll talk about later in the future. Tying that into limits and how we were looking at limits before as you're approaching some value x equals a, what's going on with a graph and how you're getting closer and closer hopefully to some input. And tying in this formal definition of a limit. So I typed these notes up and pulled some cool things before and a course that I had taught. I can download these notes into the Canvas page so that you can have them, so you don't have to worry about trying to write everything down right now. But let's go through this. And so here is what exactly the formal definition of a limit is and how we're going to prove things using the delta epsilon proof. And so that video you saw didn't give any examples of how to do that. So we're going to look at this definition. In blue, this box says, let f of x be a function defined on an interval that contains some value x equals a, except possibly x equals a. Then we say that the limit as x approaches a of f of x is equal to L if for every epsilon that is bigger than 0, there is some delta number greater than 0, such that f of x minus L is less than epsilon whenever 0 is less than the absolute value of x minus a, which is then less than delta. Okay, so kind of confusing, and to me it seems a little bit confusing, but let's go through and actually say what that is meaning geometrically. And then I think that it hopefully isn't too bad. Okay. So what the definition is telling us. So maybe you're a skeptic. You're told that you're looking at a limit as x approaches some number of a function, and you are telling your friend, when I get really, really close to this number, that function is going to give me this. And well, your friend said, well, what if you want to get a little bit closer than that? Can you still get closer to that y value? And so they might keep challenging you to get closer and closer to that epsilon value. And could you find some value in that input that's going to give you close to that L? Okay. So here we have this graph, and they choose some epsilon. And so we're going to go up epsilon from that y value, and we're going to go down epsilon from the y value that we're approaching. So notice here on this graph, as x is getting closer and closer to a here on the left, and closer to a on the right, that y value that we got was L. So if you gave some value of epsilon, notice that what you're going to do is basically make some horizontal line, a horizontal line at L minus epsilon and a horizontal line at L plus epsilon. And if you look at it that way, once you hit the graph, in this case, it looks like it didn't go all the way. Oops. So once I hit the graph of that horizontal line, we're going to extend down to the x-axis. And so you're going to say, well, if you choose epsilon close to L, then we can choose some value here that's close to A that we're going to be within what we wanted you to be within. And so notice if you choose any value in here from A minus delta or A plus delta, that we would fall within that yellow border, which we wanted to. So any point I came up on here would be in the yellow. And so I would be within epsilon distance of L. So if you're given the epsilon, we can find some delta, if that limit exists, to be within the borders that we wanted to be within on that L. So let me kind of go back and read what I had typed before, and I might be repeating a little bit of what I just said, but it doesn't hurt to hear it a couple times. So what the definition is telling us is that for any epsilon greater than 0 that we can go to our graph and sketch two horizontal lines at L plus epsilon and L minus epsilon as shown on the graph above. Then somewhere out there in the world is another number, delta, which is also bigger than 0, which we will need to determine. Okay. That will allow us to add in the two vertical lines to our graph at A plus delta, A minus delta. If we take any x between those two vertical regions, then and show that we're in that horizontal, then as x, so then this x will be closer to A than either A plus delta or A minus delta. Or we could say the x minus A, the absolute value of that is less than delta. So if we identify a point on the graph that a choice of x gives, then this point on the graph will lie in the intersection of the vertical and horizontal region. This means that this function value, f of x, will get closer and closer to A than either of L plus epsilon and L minus epsilon. Or the absolute value of x minus L, that has to be less than epsilon. Okay, so if we can take any value of x on a vertical region, then the graph for those values of x will lie in the horizontal region. So notice there are actually an infinite number of possible deltas that you can always choose. In fact, we can go back and look at the graph above. It looks like we have taken a slightly larger delta than gotten on the graph from the vertical region to be completely contained in the horizontal. So right here, like I showed before, I had noticed that when I go on the horizontal and hit the graph, it actually extended past the delta we ended up choosing to make sure that we were within that yellow region. So we technically could have chosen delta to be a little bit bigger here and still be within the region we wanted it to be in. So also notice, as the definition points out, we need to make sure that the function is defined in some interval around x equals a, but we don't really care if it's defined at x equals a. So we saw before open circles at a point. That doesn't mean that the limit won't exist there. Remember that the limit, we do not care what is happening at the point. They only care what is happening around that point in question. Okay, so we're almost ready to jump in and try to do one of these delta epsilon proofs, but just kind of a reminder, because we are going to be working with absolute values and inequalities. So just a reminder, when you have an absolute value and it's less than some number, you can drop those absolute values by sandwiching it. So this one, in this case, this would be negative 0.1, then it has to be less than x minus 3, which is less than 0.1. So any number in this range would work for x. And so we want to solve for x. And so if we add both sides, we add 3. Well, we have, let me do some side work over here. We have 3 really minus 0.1. I'm going to add a decimal and a 0. So I'm going to have to borrow. So this gives me 2.9 is less than x is less than, and 3 plus 0.1 is 3.1. So this is telling me, when we're going to look at these examples, is I'm trying to sandwich the values I choose for x to be around 2.9 and 3.1. And if we're thinking about limits and it existing, then any value that you chose in between here should fall in that region of your output of L plus epsilon or L minus epsilon. Thank you. And so this is wait. No, so that should be positive 2.9. Okay, so looking back here, we're going to kind of walk through this again. And I kind of put it in so that I'm walking you through kind of steps at first to kind of see how to do this process. So what we're going to do, all we're trying to do is, if we want to get really, really close to y equals L, then there's some epsilon that will be close enough, and you can choose delta to get you in that interval. This is just like the notation of closeness and how close you want to get. Okay, so while understanding that we want what it means for a limit to approach some value of x. Okay, so we want to show that if we took the limit as x approaches 4 of 2x plus 3, we get 11. So this was so much easier if we just did what we did yesterday, right? Basically, this is saying I can go in, because this is a polynomial, and there was a theorem that said if you have a polynomial, you can just go in, and wherever you see an x, you're going to plug in what value you're going to. And so in this case, this would be 2 times 4 plus 3. Oops, something's wrong. 2 times 4, yeah, that's right. 2 times 4 is 8 plus 3, which gives us 11. But we want to go through the rigorous proof of this, and we're not going to do this very much. This is pretty much the only section we're going to talk about this rigorous proof and having to do this. So don't get too freaked out. So we're going to say let f of x, as x approaches a, of f of x equals L. So in our situation right here, our f of x value, what we're taking the limit of, notice, is this 2x plus 3. The limit that we're approaching, this is our L value. And the a value, we're looking at x getting closer and closer to 4. So here our a value is 4. Okay, so rewriting this. So we said that a was 4. We said that f of x was just the 2x plus 3. The value that we were approaching As x goes to 4, the L value was 11. So we're just going to go back in and plug in what we have for A, f of x, and L into this definition. Okay, so we're looking at this definition right here. I have f of x minus L. So using what we just defined before, we said that f of x was 2x plus 3 minus L, and L was 11. In that absolute value, we want this to be less than some epsilon. Whenever 0 is less than, so we're going to just rewrite this out with what we have. So 0 is less than the absolute value of x minus a, but a in our case, we're going to 4. This has to be less than some delta. So when doing these, we're kind of waving our hands. We're trying to manipulate, in this case, we're going to try to manipulate this left-hand inequality to look similar to this right-hand inequality. That's kind of like the side work that you're doing, and then it's weird, you kind of, for the proof, you actually go backwards. You start with the delta piece, saying, hey, I did find some delta that would get you back over here to this epsilon. Okay, so like I said, that our goal right there is to manipulate that f of x minus L to look like the absolute value of x minus a. So I'm just going to rewrite this epsilon value for this inequality. So we have 2x plus 3, the absolute value of that, minus 11 is less than epsilon. So notice if we combine like terms in our absolute value, it actually just kind of falls out in this case. And it doesn't always do this, unfortunately, but in this case it does. 3 minus 4, actually it's not quite there yet. 3 minus 4 is negative 8. So we have the absolute value of 2x minus 8 is less than epsilon. So notice that there's a 2 in common in both terms, and so let's factor that out. And so factoring out that the 2.
So you swapped the 11 for the 4?
What I did, I didn't swap the 11 for the 4. What do you mean swapping the 11 for the 4? There's 2 separate.
Oh, you just simplified it.
Yeah. Yeah, so right here I just said 3 minus 11 gives us the negative 8. And then here we'll pull out a 2 from both terms, which would get x minus 4 in the parentheses. Absolute value is less than epsilon. Well, 2 is always going to be a positive number, right? And so it doesn't matter if that 2 is inside that absolute value or outside that absolute value. And so we can pull that 2 outside the absolute value. And so we have 2 times the absolute value of x minus 4, which is what we are trying to get in to look like over here, is less than epsilon. And so if we divide both sides by 2, we get the absolute value of x minus 4 is less than epsilon divided by 2. So this has told us what we need to choose our delta to be. So if they gave us some value of epsilon, we're going to choose our delta to be half that value, and that will make sure that we're within those bounds of the output of L plus epsilon, L minus epsilon. Okay, so we want to choose delta to equal epsilon divided by 2. Okay, so for choose delta what you got on the right-hand side of the inequality. In our case, we just said epsilon over 2. So what we just did was scratch work of our proof. And so now the proof is actually going backwards, like I had stated. And we're going to first start with the absolute value of x minus 4 is less than delta. And then we're going from this point, going the opposite direction. We're trying to find what we're starting with. We're trying to manipulate this. And so once we've done that, we are done. Okay. So we're going to start with, like I said, x minus a is less than delta, and we want to show f of x minus L is less than epsilon. Well, in our case, our a value again was 4, so we want to get x minus 4 is less than delta. We want to show that f of x, well, remember f of x was the function 2x plus 3. Minus L, which was 11, it was approaching an 11, is less than epsilon. Okay, so proof. We're going to let delta equal epsilon over 2. So the absolute value of x minus 4 less than delta, well then that means that epsilon, absolute value of x minus 4 is less than epsilon over 2. Well, I can isolate epsilon by multiplying both sides of this inequality by 2. And so doing that, we get 2 times the absolute value of x minus 4 is less than epsilon. Well, again, kind of the same reasoning from before when I pulled out the 2. 2 is always positive. We can pull it outside the absolute value. It doesn't matter. We can put that 2 inside the absolute value. And so this is the same thing then as 2 all times x minus 4 has to be less than epsilon. So let's distribute that 2 inside the parentheses, which is inside the absolute value. And so we have the absolute value of 2x minus 8 is less than epsilon. But our goal, remember, was to get it to look like 2x minus 11. And so we're just going to rewrite this negative 8, and we can manipulate negative 8 to look like 3 minus 11. Okay, so we want to rewrite negative 8 to get the inside of the absolute value. To look like f of x minus L, or in our case, 2x plus 3 minus 11. And so again, we're just going to rewrite it. This is the absolute value of 2x minus, well, we can rewrite that as 3 plus 8. I'm sorry, 3, and I said it wrong. We can rewrite that as positive 3 plus 3 and minus 11. is less than epsilon. So we just showed that f of x minus L was less than epsilon. Okay, so linear ones are a little easier than if we had a higher degree polynomial. So we have time, I think, to do one more linear, and then we'll look at tomorrow maybe doing some that are not linear. Let me blow that up. Okay, so we want to use the delta epsilon proof to show that as limit as x is approaching -3, we would get back -30. Sorry, limit as x approaches -3 of 7x minus 9, we get back -30. And you can see that if you do direct substitution, that's exactly what you get. And so we want to prove again there exists some epsilon greater than 0 such that the absolute value of f of x minus L is less than epsilon. There exists a delta which is greater than 0 such that absolute value of x minus a is less than delta. So we're going to first start with our scratch work. And then we're going to go in the reverse direction. So our f of x, that's what we're taking the limit. And so looking at this, we have the absolute value of f of x, but f of x is 7x minus 9, minus L. So that's where we're approaching. So minus a -30. And that absolute value has to be less than epsilon. And we're trying to manipulate this. So try to get this to look like x minus a, but we have x minus a -3. Our a value in our case is -3. If we want, we could rewrite this a little bit, right? X minus a -3 is the same thing as x plus 3. Okay, so let's just start simplifying. Inside the absolute value, let's rewrite it. So this is 7x minus 9 minus a -30, which is really plus 30. So we have 7x, a -9 plus 30 gives us plus 21. I have to bring down my less than epsilon each time. And I'm trying to manipulate it to look like this. I noticed that 7x plus 21 both have a 7 in common, so we can pull that 7 out. Pulling that 7 out of both terms, we get x plus 3. And this is less than epsilon. And now if we pull out the 7, divide by the 7, we can say the absolute value of x plus 3 has to be less than epsilon divided by 7. Okay, so we determined what we're going to let our delta be. So you give some number. So you say, hey, I want you to get between just a 1 unit on the left or the right of that value that you're coming. Then I would choose my x value around this value of, where was I going, x equals -3, I would choose it to be, you gave me epsilon to be 1. I would go 1/7 to the left and 1/7 to the right, of that value. And that's how I would do it. So delta is equal to epsilon over 7. But then if you said, hey, I want you to get closer than just 1 unit to the left or above or below that y value we're going to, let's say you said 0.1, then I would just say, well, then my delta is going to be 0.1 divided by 7. And I'm going to add that and subtract that from my -3 to get my interval around that x equals -3. Okay, so proof. We want to choose delta to equal to epsilon over 7. And so we are going to show that if we have x plus 3 less than delta, which in our case is epsilon divided by 7, and then we want to manipulate this to look like the f of x minus L inside the absolute value. Let's multiply both sides of this inequality by 7. And so we have 7x plus 21 inside the absolute value is less than epsilon. We can factor that 7 out of both of those terms. Wait a minute, do I want to factor the 7 out? No, I don't. Let me just go back up to see what I had to, I forgot what I was trying to make it look like. We're trying to make it look like 7x minus 9 plus 30, or minus a -30, either way. And so notice that -9 plus 30 is another way that we could write 21. Let's do the minus -30, because it's really minus L, and L was -30. And so we just showed it that this is f of x minus L ended up being less than epsilon. Okay. So let's stop there. This would be very similar, and I might not do this problem tomorrow, or maybe I'll let you guys try it on when we start. But we'll go into more detail of some more harder problems where it's not a linear problem and how to deal with those and kind of manipulate it to look like we were doing. But it's kind of, you know, like I just said, it's kind of waving your hands, manipulating something to look like something else, and then kind of working backwards. So hopefully that wasn't as bad as I was projecting that it was going to be. And that just made so much sense to you. So let me stop the video.
I'd say it definitely made